Why do atoms connect to form molecules? Why does oxygen pair with hydrogen to create water, or carbon combine with other elements to build the chemistry of life? The answer lies in one of the most fundamental principles of chemistry. Atoms bond because stable energy arrangements are favored by the laws of physics. This is Mattermosaic, piecing together the universe, one discovery at a time. Today we explore why atoms bond, and how these connections build everything from simple gases to the complex molecules inside living cells. Atoms consist of a nucleus surrounded by electrons occupying specific energy levels. Think of these levels like shells. In the early 20th century, scientists began to understand that the behavior of electrons, particularly those in the outermost shell, determines how atoms interact. A key idea came from Gilbert N. Lewis in 1916. Lewis proposed that atoms tend to arrange their electrons so their outermost shell becomes stable, often resembling the electron configuration of the famously stable noble gases. This concept became known as the octet rule. While it's not a universal law, it's a fantastic starting point for understanding many chemical bonds. So why do atoms bother forming bonds at all? Because doing so lowers the total energy of the system. In physics, systems naturally move toward more stable, lower energy states. When atoms share or transfer electrons, the combined structure can become much more stable than the separate atoms floating around on their own. Let's look at the most common type of bonding, the covalent bond. Here, atoms share pairs of electrons. This sharing allows both atoms to effectively fill their outer electron shells. A simple example is the hydrogen molecule. A hydrogen atom has one electron. When two hydrogen atoms get close, they share their electrons, creating a strong bond that holds them together as a single, more stable molecule. The quantum mechanics behind this, first explained by physicists like Walter Heitler and Fritz in the 1920s, showed how electron wave functions overlap to create these chemical bonds. Then there's the ionic bond. In this case, electrons are not shared, but completely transferred from one atom to another. This creates positively and negatively charged ions that attract each other through powerful electrostatic forces. A classic example is table salt or sodium chloride. A sodium atom easily gives up one electron, becoming a positive ion. A chlorine atom happily accepts that electron, becoming a negative ion. These opposite charges lock the ions together in a strong, rigid crystal structure. We also have metallic bonds, which are a bit different. In metals, the outer electrons aren't tied to any single atom. Instead, they form a sea of electrons that moves freely through a lattice of metal ions. This is exactly why metals are so great at conducting electricity and heat. It's just electrons flowing through this shared sea. Despite these different types, all chemical bonds share the same core principle. They minimize energy through electron interactions, all governed by the fascinating rules of quantum mechanics. When atoms bond, they form molecules with specific shapes and properties. The geometry of a molecule depends on how the electron pairs repel each other. This is described by the VSEPR model. The idea is simple. Electron pairs, whether in bonds or as lone pairs, arrange themselves as far apart as possible to minimize repulsion. This gives molecules predictable three-dimensional structures. Take the water molecule, for instance. The oxygen atom has two pairs of electrons bonded to hydrogen and two lone pairs. These four pairs push each other away, forcing the molecule into a bent shape with an angle of about 104.5 degrees. This specific geometry is the reason for water's unique properties, like its polarity and its amazing ability to dissolve so many different substances. But chemical bonding doesn't just create small molecules, it builds enormous structures too. Carbon atoms are superstars at this. They can bond in long chains, intricate rings, and complex networks. This versatility allows carbon to form the backbone of all organic chemistry and the essential molecules of life, like proteins, DNA, and carbohydrates. Ultimately, the ability of atoms to bond is deeply rooted in quantum mechanics. Electrons don't just act like tiny particles, they also behave like waves. When atoms get close, their electron wave functions interact. A constructive overlap between these waves creates stable bonding orbitals that hold the atoms together. At the same time, other combinations of waves can form antibonding orbitals, which would push the atoms apart. A bond forms only if the stable, bonding orbitals are filled with electrons, while the unstable antibonding ones remain empty. These quantum effects determine everything about a bond, including its strength and its length. Stronger bonds generally mean a lower energy state and a shorter distance between the atoms. Bonding also explains the energy changes in chemical reactions. To break existing bonds, you need to put energy in. But when new, more stable bonds form, energy is released. This constant exchange of energy drives countless natural processes, from the metabolism inside your cells to the combustion that powers an engine. In biology, chemical bonds create the very architecture of life. The DNA molecule stores all our genetic information through a precise sequence of atoms linked by covalent bonds. Proteins fold into incredibly complex shapes that allow them to act as enzymes, structural supports, and tiny molecular machines, all thanks to the bonds holding them together. Even the materials we use every day depend on bonding. The incredible hardness of a diamond comes from a three-dimensional network of carbon atoms locked together by strong covalent bonds. The flexibility of plastic comes from long repeating chains of polymer molecules. And the strength and conductivity of metals come from their unique, shared electron structure. Although we often draw bonds as simple lines between atoms, the reality is a dynamic dance of electric forces and quantum wave behavior. Atoms are constantly vibrating within molecules. Electrons exist not as fixed points, but as clouds of probability. The bonds that hold our world together are stable, yet they are never completely static. Modern technology now allows us to observe and even manipulate these bonds in amazing ways. Spectroscopy lets us measure the energy of molecular vibrations, and scanning tunneling microscopes can actually take pictures of individual atoms and the bonds between them. Chemists can now design brand new molecules with specific properties by controlling exactly how atoms bond, leading to breakthroughs in medicine, materials science, and renewable energy. So, the simple question of why atoms bond opens a door to understanding the fundamental structure of matter itself. From the smallest molecule to the most complex biological system, chemical bonds organize atoms into the patterns that define our entire physical world. Everything around you, the air you breathe, the water you drink, the very cells that make up your body, all exist because atoms combine into stable arrangements. Without bonding, the universe would just be a vast, empty space filled with isolated atoms drifting aimlessly. There would be no molecules, no chemistry, and certainly no life. Instead, the laws of quantum mechanics allow atoms to share electrons, exchange charges, and build the infinite variety of forms we see around us. Through bonding, simple particles become complex matter. This is Mattermosaic, piecing together the universe, one discovery at a time. If this exploration changed how you think about the invisible forces holding matter together, share it with someone curious about the chemistry shaping our world. Let us know in the comments which hidden process of nature you'd like us to explore next. Thanks for watching.